So we are learning the particle on a sphere, how to solve the Schrodinger wave equation for the particle on a sphere. We already solved the Schrodinger wave equation for the system, and for that we adopted the method of separation of variables. And then we had assumed that the wave function psi is a product of two functions, two independent functions, that is psi is equal to f and the product of f and p, where p is a function of theta and f is a function of phi. Okay, so we had separated the variables and then we solved for p theta and we solved for f theta, f of phi, and we know the solution for this p of theta and f of phi. We first solved for f of phi because that was the easiest solution, and f of phi is equal to, there are several solutions like 1 by root pi into sine m phi by root pi cos m phi, then 1 by root 2 pi e raised to plus or minus I m phi. Like that means you have the solutions in terms of trigonometric forms and solution as a complex function. So let us take the solution 1 divided by root 2 pi e raised to I m phi. I'm taking this solution for the moment now because you can express this one in trigonometric forms also, because e raised to I kx is cos kx plus I sin kx. This is a relation already, so we can convert this complex function in terms of trigonometric functions as well. So using this one and the other trigonometric solutions are equivalent. So this is f of phi, and the other solution is, this is a normalized function. You know that 1 by root pi is a normalization factor, and the other function is p of theta, and the solution of this was associated Legendre polynomial. You remember this, PLM x or PLM cos theta, PLMx or PLM cos theta. We already learned the expansion of this PLM cos theta, and we already derived the different functions for different values of L and M. Here M is the absolute value of M in this equation. So this is p theta, and there is a normalization factor that should be included, that is normalization factor n, and the value of n is equal to 2l plus 1 divided by 2 into l minus m factorial divided by l plus m factorial, the all raised to 1 divided by 2. That is a normalization factor, 2l plus 1 by 2, l minus m factorial divided by l plus m factorial, the all raised to half. You have to note here that we are taking the absolute values of the quantum number m here. Okay, so that is the normalization factor. Now we know f of phi and p of theta. So psi is equal to p theta into f of phi, that is the product of these two. So that will give the complete wave function. So the complete wave function psi theta phi, psi is function of both theta and phi, theta phi is equal to n is a normalization factor of this p theta or associated Legendre polynomial, n PLM cos theta, PLM cos theta, that is the p theta function, into f of phi. F of phi is 1 divided by root pi, root 2 pi, 1 divided by root 2 pi into e raised to I m phi, So we have two quantum numbers here, L and M, in this equation. So psi depends upon both L and M. So we can write psi L M. Okay, psi L M. It means that psi depends upon both quantum numbers L and M. So psi lm theta phi is this one. We have the expression for the complete wave function. So now we can try to solve for the complete wave function for few values of L and M. Let's take few values of L and M. For example, let me write a column here. In the first column I will write L. I will write L here in the first column. L here in the first column. L here in the first column. Then I am going to take M in the other column. M here. And for different values of L and M, we will find out what is the value of psi theta phi. Okay. So we will find out psi theta phi. And for psi theta phi, we must know, see, that is the first one that we have to know is n. N is the normalization factor for the associated Legendre polynomial. So in one of the columns I will include the value of n also. Let me include the value of n here. N you can easily solve for n, because if you know L and M, then you can find out n. It's a simple equation. You can do it yourself. I will only furnish the values of n here, and for each value of L and M, you can try how you get the value of n from this equation. Okay, and then I will give in the other column PLM cos theta. I don't need to elaborate it here, because in the last lecture I already explained how to find out the PLM cos theta. So in this fourth column I will put PLM cos theta here, and then we have PLM cos theta. Then we need the last 1 by 2 pi into root im5, we have to multiply with this one, so we will get a psi lm theta phi. So in the last column I will put psi lm theta phi. Here let me put psi lm theta phi. Okay. So let's find out the values of psi lm theta phi for different values of L and M. Let me put the value of L as 0, L is equal to 0, and M is equal to 0. L is equal to 0 and M is equal to 0. And for L is equal to 0 and M is equal to 0, you can find out what is the value of n. Then it will be like 2L plus 1 divided by 2. Here in place of L you have to substitute 0, that is 0 plus 1 divided by 2, that is 1 by 2, into L minus some factorial divided by L plus some factorial. In this case it is 0 minus 0 factorial, means 0 factorial divided by 0 plus 0 factorial, means 0 factorial. 0 factorial by 0 factorial, that is equal to 1. So you have a root of 1 divided by 2, that is 1 divided by root 2. So your n is equal to 1 divided by root 2 here. Okay, and for L is equal to 0 and M is equal to 0, PLM cos theta, you have already learned this. PLM cos theta for L is equal to 0 and M is equal to 0 is equal to 1. We have already done this in the previous lecture. You can check back your records. Okay, that is PLM cos theta is equal to 1. And now corresponding to this, L is equal to 0 and M is equal to 0, we can find out what is the value of psi lm theta phi. So psi lm theta phi is equal to, what is psi lm theta phi? N into, n is equal to 1 divided by root 2, 1 divided by root 2 into PLM cos theta. PLM cos theta is equal to 1 into 1 divided by root 2 pi, 1 divided by root of 2 pi, e raised to im phi, e raised to im phi. M is equal to 0 here, that is therefore e raised to 0. Okay, that is it. So that is 1 divided by root 2 into 1 into 1 divided by root 2 into e raised to 0. E raised to 0 is 1. So the answer is 1 divided by root 2 into 1 divided by root of 2 pi, that is equal to 1 divided by root of 4 pi, or you can write that is equal to 1 divided by 2 into root pi, 2 into root pi. Okay, so that is the value of psi lm theta phi for L is equal to 0 and m is equal to 0. So we got the complete wave function for a set of quantum numbers L is equal to 0 and m is equal to 0. And like that we can find out the values of this complete wave function for other set of quantum numbers. Let us take the other set. L is equal to 1, L is equal to 1 and m is equal to 0. M is equal to 0. You already know that the value of m depends upon the value of L. We already learned this in the previous lectures, because L determines the value of m. The values of L are m are minus L to plus L through 0. Okay, so for 1, L is equal to 1, the possible values of m are minus 1, 0, plus 1. So let us take middle value, that is 0. So L is equal to 1 and m is equal to 0. And when L is equal to 0 and m is equal to 1 and m is equal to 0, you can calculate the n here. You can put L and m here, and here you are putting the absolute value of m. Okay, so you can calculate the n, and you can calculate that n is equal to root of 3 divided by 2. And for L is equal to 1 and m is equal to 0, you know what is the value of PLM cos theta, that is equal to cos theta. You have already done this. Okay, cos theta. So the complete wave function in this case is equal to n, that is root of 3 divided by 2 into PLM cos theta. PLM cos theta in this case is cos theta into 1 divided by root 2 pi, 1 divided by root 2 pi into e raised to im phi. E raised to im phi in this case is e raised to 0, because m is equal to 0, that is equal to 1. Okay, that is, therefore the complete wave function in this case is 3 by 4 pi, 3 divided by 4 pi raised to half cos theta. 3 by 4 pi raised to half cos theta. See, this is root of 3 by 2, it is root of 1 by root pi, so that is 3 divided by 4 pi, 2 into 2 pi, that is 4 pi, 3 in the numerator, 3 by 4 pi raised to half cos theta. That is the complete wave function for L is equal to 1 and m is equal to 0. And we can now find out L is equal to the wave function for L is equal to 1 and m is equal to plus 1, another possible value of m, that is plus 1. So in this case you can calculate that n is equal to root 3 divided by 2, root 3 divided by, it is not root 3 by 2, it is root 3 divided by 2. And in this case the PLM cos theta, you have already done this, the PLM cos theta in this case is sin theta. Therefore psi lm theta phi is equal to root of 3 divided by 2 into sin theta into 1 divided by root of 2 pi into e raised to I m phi. M in this case is 1, therefore e raised to I phi, okay, that is equal to, let me solve this here. It is equal to 3 by 8 pi, 3 divided by 8 pi raised to half sin theta e raised to I phi, 3 by 8 pi raised to half sin theta e raised to I phi. Okay, that is it. Then we can find out for another set of values, that is L is equal to 1 and m is equal to minus 1. Okay, that's the other column. Let me extend the column a little bit down. Okay, L is equal to 1 and m is equal to minus 1. And in this case Okay, in this case we have the normalization factor is equal to root of 3 divided by 2. You can note that we are taking the absolute value of m in this expression. Therefore, even if it is plus 1 or minus 1, this is not going to change. Whatever value we got here, we will get the same value here. Okay, because for absolute value of m in this case is 1 and 1 here. So this is normalization factor, and PLM cos theta also is sin theta, because there also we are considering only the absolute value of m, that is also sin theta. Therefore, in our psi lm theta phi is equal to 3 by 8 pi raised to half sin theta e raised to minus I phi, because it is e raised to im phi. M in this case, it is not absolute value that we have to put here. We have to put the real value, that is e raised to minus im phi, because m is equal to minus 1. So e raised to minus im phi. So we have the complete wave function for L is equal to 1 and m is equal to minus 1. Let me put here, if you are interested, you can find out the value for more values of L and m. It would be good if you do this, but let me limit the explanation to the complete wave function for the set of quantum numbers which are limited to these values. Okay, and now we have the complete wave functions. Here you can note that the complete wave function, the first one, the complete wave function for L is equal to 0 and m is equal to 0, the complete wave function is 1 divided by root of 2 pi. That's a real value. The second one for L is equal to 1 and m is equal to 0, and that is also a real function. But whenever m gets some non-zero value, then the complete wave function contains some complex function, e raised to I phi, e raised to minus I phi. These are complex functions. Okay, and in this case, if it is a complex function, the problem is that we cannot get a real pictorial representation of these complex functions. So somehow we have to convert this to real functions. But it's a blessing that in quantum mechanics we have an option for this, because you have to note here that here this is L is equal to 1, L is equal to 1, and L is equal to, last three functions have L is equal to 1. Okay, and what about the energy corresponding to these three functions, last three functions? And we have learned already that when we were giving the expression for beta, the beta's expression was beta is equal to L into L plus 1, which is equal to 8 pi square m r square divided by h square into e. We have already learned this, you know this. Okay, so this is beta, and from this beta's expression we can get an expression for e. Therefore e is equal to h square divided by 8 pi square m r square L into L plus 1. This is the expression for energy. Okay, and from this one you can see that the energy depends only upon L, not upon m. A quantum number L and not depend upon the quantum number m. Don't confuse it here, because you have an m here in this expression, there is an m here. See this one, that is not the quantum number, but it is the mass of the particle. That is not quantum number. Okay, so the only one quantum number in this expression for energy is L. So the quantum number m doesn't determine the energy, but the quantum number L only determines the energy. Therefore, in these three functions, the last three functions, you have the same value L, 1, 1 and 1. Okay, same value of L. It means that all the three functions, last three functions, represent the same energy value, corresponds to the same energy value. Or in other words, you can say that these three functions have the same energy, or they are degenerate functions. They are degenerate functions. these three are degenerate functions. These three are degenerate functions. What are degenerate functions? Degenerate functions are those state functions which are represented by different wave functions, but they correspond to the same energy value. And these are different wave functions, but it corresponds to same energy value, so these are degenerate functions. And what we are going to do now is that we know that these final two functions are complex functions, and I am going to convert these complex functions to real functions by linear combination of these complex functions. And in quantum mechanics, we know that if we are taking the linear combination of any two functions having the same eigenvalue, you will get a function which has the same eigenvalue. The eigenvalue doesn't change. So if you are taking the linear combination of this third and fourth function, you will get a new function, and this new function will have the same eigenvalue of these two functions. The eigenvalue here is nothing but the energy value, because our eigenvalue equation is h cap psi is equal to E psi. The psi represent the wave function. There are a set of wave function corresponding to different set of quantum numbers. So this is a wave function. This is also the wave function of the same Hamiltonian. So if you are taking the linear combination of these two wave functions, you will get a function which has the same eigenvalue represented by these two wave functions. So there is no problem even if you are taking the linear combination, because the energy is not going to change. Okay, so let us take the linear combination of the first two functions. The first two functions linear combination, let me call this as positive linear combination. So I am going to represent this as psi plus positive linear combination. Psi plus represents that it is the additive linear combination of the first function, this third function, and the fourth function. In this case, that is this one. This corresponds to psi 1 1, right? Psi lm. In this case is psi 1 1. This is psi 1 plus 1 theta phi. This is this function. This is psi L is equal to 1, m is equal to minus 1, psi 1 minus 1 theta phi. So we have two functions, psi 1 plus 1, psi 1 minus 1. I am taking the linear combination of this one. So linear combination in such a way that I am going to add these two functions. So that is why I am giving the symbol psi plus. So psi plus is nothing but psi 1 plus 1 plus psi 1 minus 1, the additive combination of these two functions. And obviously we have to put a normalization factor here, the normalization factor here. Okay, so psi plus is the normalization factor into additive combination, additive linear combination of the psi 1 plus and the psi 1 minus 1. And this is equal to psi plus is equal to n into psi 1 plus, that is this one. What is that? 3 by 8 pi raised to half sine theta e raised to I phi. And psi 1 minus 1 is also 3 by 8 pi raised to sine theta e raised to minus 1. So they have a common factor, 3 by 8 pi raised to half sine theta. Let me put it here. 3 by 8 pi raised to half sine theta, that is a common factor. And then what is not common are e raised to I phi and e raised to minus I phi, so they have to be added together. E raised to I phi plus e raised to minus I phi. Okay, so you already know this is e raised to I phi plus e raised to minus I phi. What is it? You already know that e raised to I kx is equal to cos kx plus I sin kx, and e raised to minus I kx is equal to cos kx minus I sin kx. We know these relations. So using these relations, I am going to expand this to the trigonometric forms. So In our case, we have the normalization factor n into 3 by 8 pi raised to half sine theta into e raised to I phi plus e raised to minus I phi. So e raised to I phi plus e raised to minus I phi, what is that? That is equal to e raised to I phi is cos I phi plus e raised to plus I sin phi. I will write it here. Cos I phi plus I sin phi plus e raised to minus I phi. E raised to minus I phi is equal to cos I no, it is not cos I phi, cos phi only. Cos phi plus I sin phi plus e raised to minus I phi is equal to cos phi minus I sin phi. So this 2 will be cancelled. So what we have here is 2 cos phi. So we have n into 3 by 8 pi raised to half sine theta into 2 cos phi. That is equal to n into, it's equal to, let me write it here, or I will write it in the other page. We don't have enough space here. That is equal to that is psi plus is equal to 3 by 2 pi raised to half 3 by 2 pi raised to half sine theta cos phi. Okay, sine theta cos phi. So we have there is an n also, normalization factor n. The normalization factor n's value is nothing but 1 divided by root 2. So we have 1 divided by root 2 into 3 by 2 pi raised to half sine theta cos phi, that is equal to 3 by 4 pi raised to half, 3 by 4 pi raised to half sine theta cos phi. So that is psi plus 3 by 4 pi raised to half sine theta cos phi, psi plus. Let me put that in a box because this is very important. Psi plus is equal to 3 by 4 pi raised to half sine theta cos phi. And now we can find out psi minus. Psi minus is equal to normalization factor n into psi 1 plus 1 minus, that is a subtractive combination, psi 1 minus 1. Okay, and that is equal to n in this case is 1 divided by root of 2 into I into 3 by 8 pi raised to half sine theta, that is a common factor, into e raised to I phi minus e raised to minus I phi, e raised to I phi minus e raised to minus I phi, and that is equal to e raised to I phi minus e raised to minus I phi is equal to 2i sin phi. You can see that in the 2i sin phi. So that is equal to 2i divided by root of 2 into I 3 by 8 pi raised to half sine theta, what was e raised to I phi minus e raised to I minus I phi, 2i sin phi. 2i I already wrote here, what is remaining is sin phi, and that is equal to 3 by 4 pi raised to half sin theta sin phi, sin theta psi. This is psi minus. So that is another expression. Psi minus. What is it? Not psi 1. Psi minus. Psi minus is equal to 3 by 4 pi raised to half sin theta sin phi. Psi plus is equal to 3 by 4 pi raised to half sin theta cos phi, and this is 3 by 4 pi raised to half sin theta sin phi. And I will explain how to interpret these things in the next video.